My calculator is flying around, so we'll be able to just quickly run through these things. Can somebody punch in the values for the different numbers and start calling them out? While they're doing that, I want to show you guys something. This pendulum here, if I pull it up to a certain height, call it this height here, what have I given it?
You've given it potential energy.
Potential energy. It now swings down. At the bottom here, what does it have? Kinetic energy. It then swings back up, and I'm going to ask you guys to move now. And what does it have here? Potential energy. Does it have any kinetic energy?
Yes.
Does it have the same potential energy as it had back there?
Yes.
Exactly. And then it swings back down again, and now what does it have?
Kinetic energy.
And back to the top, what does it have here?
Potential.
Can it come any higher?
No.
No, because
It lowers.
you can't get any energy from nowhere. So the thing cannot come any higher because it can't just get energy out of nowhere.
Okay.
So let's put it to test. Alright, to move out of the way. So what's going to happen is if this thing comes any higher, it'll hit me in the face, right?
Yes.
Yes.
Alright, so I'm
But it won't hit you in the face coming back.
I'm putting my body on the line for you guys.
That's potential energy. So.
I bet you it will not come back and hit you in the
Kinetic.
face.
Kinetic energy,
Potential.
okay? And it comes back up again.
Oh.
Yes.
And it's kinetic energy. And what happened is it comes up to potential energy and it stops. It can't get energy out of nowhere. And that's the thing with this conservation of energy. It'll start, it'll go through, the energy will change, it'll go up again, but it doesn't make energy out of anywhere.
it
Okay?
kind of
The
reduces.
energy just stays the same. It just changes form from potential energy to kinetic energy to potential energy. Now you've used the fact, and we've used the fact, that energy changes form to calculate the speed that this thing is going to reach at a certain point. Okay, so now we're going to test that. We're going to have to see if we can get to the correct answer.
Right.
Cool. Okay, what have we got here? We've got an equation that gives us the height that we need and for different velocities. But do we know which velocity to plug into this equation?
No. Oh yes.
So all we need to do is take the 1.5 and put it in place of v. Take the 1 and put it in place of v. And take the 0.5 and put it in place of v. And then we can get our height for the different velocities that we need.
Aha.
This is 0.051, the other said straight 11.
No? That's great. So that's 0.051 meters, which is how many centimeters? 0.051 meters is how many centimeters?
Is it centimeters?
Okay?
Is it centimeters? There's 3 digits after the comma.
Okay, how many centimeters in a meter? 100. Okay, 1,000 millimeters in a meter. 100 centimeters in a meter. So if we got 0.051 meters,
It's 51 centimeters.
it's we move the comma 1, 2 places. So write it out for you guys. 0.051 meters. We move the comma how many places for 100?
2.
2 places. 1, 2. So we have
1, 5,1.
5.1 centimeters.
500.
Because everything divided by itself is
Okay, so you're right. So can you do the last one for green team? So, do you know the height that we're looking for is the difference in height from its rest position here
Yes.
to the height that it reaches up here. So if we can measure this height, the resting height, alright,
Oh, okay.
and then we just add the height that we need, we can then
To the
take it to
velocity
the correct
switch.
spot and it'll swing.
That was it.
So all we need to do is figure out what is the height here. So we just need a piece of string now.
Of the middle.
Actually, just measure it from the bottom. It'll make your whole thing accurate.
Okay.
Okay, so now to get 1.5 meters per second, how many centimeters do we have to add to that
11.
height?
11.
We have to add 11 centimeters. So can you add 11 centimeters?
And then just take a mark from where you held.
Okay, so from that mark, he has to add 11 centimeters. So do it. Great. Can I explain to you guys how we're going to measure the actual speed of this thing? How are we going to measure the actual speed of this thing as it swings down the bottom?
We are going to do that.
checkerboard and-
After
We're going to
the
use this
division.
checkerboard, exactly. So I've got my iPad set up at the back there.
Okay.
What's going to happen is we're going to take a video of the pendulum swinging past.
And then it's gonna send it to the.
Okay, we're going to have a look at the different frames of the video. So what happens when the pendulum swings past, for example, this point? Okay, we'll pause it there and we'll have a look. We'll then have a look and we'll pause it there.
Okay.
So what has it done in this displacement here? What has it actually covered?
Meters per second.
It's covered a distance.
Yeah.
Okay, but we've got a stopwatch here to time how fast it's going to do that. We've also got a stopwatch on the iPad so we can time how fast it covers the actual displacement. And then from that, what is your formula for speed?
It is.
You got a chance?
Distance multiplied by over time.
Distance divided by time. So if we have a distance and we have a time, what can we do?
You can use it to calculate.
Calculate the speed, and hopefully, if we've done the experiment correctly, what is our speed going to come out to be?
1.5 meters per second.
1.5 meters per second.
Or close.
Or very close.
Yes.
But why is it not going to be exactly 1.5 meters per second?
Would it affect because we used instead of 9.8 for our gravitational pull, if we use 10?
One very good reason. Okay, so we didn't use an exact gravitational pull, right? You
Next
got
thing
another
when
one.
you like, it's more like when you draw a graph.
Yeah.
You are marked according to line of best fit.
Yeah.
Oh yes.
So that number you were told to find is an approximate number. So you have to find something close to that.
Okay.
Rounding off.
We've done a little bit of rounding off. Agreed.
Yeah.
Okay, so a little bit of rounding off is going to affect our answer. Are we going to pick this thing up to exactly 11 centimeters?
No.
So we're going to be as close to 11 centimeters as possible, but we might get something a little bit wrong, and that introduces a little bit more error. So we're going to try and get as close to our 1.5 meters per second as possible, but it might be in a ballpark figure. So we'll see how close we can get. So you got the first line, the second line. So you need to just bring it down a little bit. Okay, there. And see what it does. Cool. And so we got our video capturing it. We go to the table and see if we're right. Okay, let's go, guys. So what we can see now is in slow motion, the pendulum swinging past our starting point, or the bottom of the swing there. Guys, happy with that?
Mm-hmm.
So what we're going to do is, in this slow motion view, we're going to try and capture a time and capture a distance that it traveled, so we can get a basic snapshot of how fast it was traveling at the bottom of its swing. And we're going to see how close that came to 1.5 meters per second. Okay. So we're going to get fairly close to the bottom of the swing. Going to zoom in as much as possible. Each of these stripes is 2.5 centimeters. I just measured that out beforehand. So we're going to draw a line to start off with there. Happy with that, guys?
Mm-hmm.
The next thing we're going to do is put a timer on the screen. Okay, it's going to time the time it takes for this thing to swing a little bit. And it's going to swing past. Oops, sorry. It's going to swing past a little bit, and we'll stop it maybe there. Okay, so now, who can count for me the number of stripes in between that?
6, 7.
Okay, 1, 2, 3, 4, 5, 6, 7 full stripes, and a little part of the black stripe. Each of the white stripes is 2.5 centimeters. Each of the brown stripes is 2.5 centimeters. So how far did we travel? 5 times 7. Okay, so 2.55. So each of the white stripes that you counted is actually then counting as 2.5 plus 2.5, because you only counted white, white, white. So we've got 35 centimeters plus, call it a quarter of the brown stripe, which is a quarter of 2.5, about 0.5 centimeters. So we've got about 30.5 centimeters traveled. How far is that in meters? Shanli? How far is 30.5 centimeters in meters?
Do you have to divide it by 100? Okay, but can I have a calculator, please?
You don't have to have a calculator
I
for
don't know what
that.
it is.
You just take the decimal point when you're dividing by 100, and you can just move it to the left.
It's 3,5.
How did you get that?
You just move the comma.
There you go, you're a genius. Okay, so we have it. We have 0.305 meters traveled. And we need a time that it's traveled in. So we can have a look at our stopwatch. And what does the stopwatch say?
29.
23.
Okay, but what is the 23? Is it seconds?
Split seconds.
Split seconds, okay? So we need to adjust that. We've got this in meters. We need to make this one into. So it's 0.23. Okay, who's got a calculator for us?
It's not in your pocket.
No. Who's
It's going.
Go and get it by the math board.
1.326
Oh, never mind.
meters per second. So, did we get our 1.5?
Nope.
Not quite.
Relatively close.
What could we have done wrong? Okay, I like that. We're relatively close. We got pretty close. Okay, so I'm quite chuffed with that answer. What I want to discuss now in the last 5 minutes of this lesson, because we don't have that much more time, is about this whole idea of scientific experimentation. Unfortunately, we could only set up as close as possible to the actual proper experiment. And if we start to eliminate various factors, we'll get a much closer answer. This answer is a little bit off because we've started to introduce various things that could have affected our experiment, okay? Let's try and list some of those things. And then I also want to teach you guys a bit of a method to get a more accurate answer, and a more accurate answer, and a more accurate answer. And this is something that they will ask you in exams, so it's something worth remembering because it's a much better way of taking the experiment. So the first thing I want to discuss is we only did this experiment once. If we do it next time, are we going to get a different answer?
Yes.
Yes, we are. Why are we going to get a different answer?
Because we will
The
be
measurements
using
might be
these
more
methods.
accurate.
Okay, our measurements might be a little bit more accurate. We might have it maybe a little bit higher. So our 11 centimeters might have been a little bit not perfect. So if we measure the 11 centimeters, a bit better. Possibly there was a little bit of swing in the rope. Maybe that'll be gone. So there's going to be a different answer. What should we then do to get the answer that we'll believe? If we pick one, then all the factors that affected that one specific experiment are making a big impact on our result. So what I'm saying is we want to try and remove the different factors that could affect just the one experiment by trying to pick many, and then potentially, what if we take an average of them all?
Okay.
What is that average going to do? It takes all of the different experiments into account. So we give that one a weighting, we give that one a weighting, we give another one a weighting, we give another one a weighting. But what it does eventually over time is all the different effects, all the different errors that we got into our result will start to filter out, and we'll get a more and more accurate answer. So that's something in physics that you must remember, is if you're going to do an experiment, your numbers are never going to come out exactly as you expect because of this different error that we get. And you can start to measure it more and more accurately, and you'll get better and better answers. So our test wasn't exactly fantastic, but it got a pretty good answer. I like it. It was pretty close. If we then did it again and then averaged it, we'd get a little bit closer, possibly. If we did it again and then averaged, we get a bit closer. So you can always, and you always should, do lots of experiments and average them. You should try and remove as many different points of error as possible. Give us, just name some of the bad, the error points that we actually had today, and we've listed some of them already.
The fact that we were outside.
The fact that we were outside. So there was wind
Wind.
that might have affected us. Good.
And the rope had a bit of
use
swing.
Yeah.
The angle of the pendulum wasn't necessarily straight.
Okay.
So we could have used something maybe transparent or something to actually
Brilliant.
put
Okay,
it-
so originally when I had the pendulum hanging, that's why I had the pendulum hanging flat, because we then wanted the whole circle to move together. Hanging directly down, it could have twisted a little bit, which would have affected our...
So we
which it
twisted
did.
something
Good,
transparent almost like that
good.
would fit the pendulum and you
Good.
can swing it to that angle.
Exactly. So can you see that we need to try and think about all these things in advance? And I tried to take as many of them out of the way as possible, but we still had a lot of error coming into the experiment. Having said that, we got a pretty good answer. So what the whole point of this was to show you that if you pick it up a certain height, you let it go, you can actually calculate in advance how fast it's going to be traveling at the bottom.